Types of relations. So far we've been building our understanding of relations, what they are and different ways to show them, like using ordered pairs. Now, on this slide, we're going to take the next step and start classifying relations. Think of it like this. Just as we categorize things in everyday life, we can also categorize relations based on certain characteristics they have. These characteristics are called properties. By identifying these properties, we can better understand how different relations behave and what makes them unique. It allows us to organize our knowledge and makes working with relations much more manageable. Over the next few slides, we'll be diving deep into 4 important types of relations: reflexive, symmetric, transitive, and equivalence relations. We'll learn exactly what each of these means and how to determine if a given relation possesses that property. We'll be looking at examples to really solidify your understanding, so pay close attention to how we check for each property. These concepts build on each other, so it's important to grasp each one before moving on. Reflexive relations. So we've just discussed what relations are, how they connect elements of a set. Now, we're starting to look at types of relations, and this slide introduces the first one, reflexive relations. Let's read the first line together. It says, a relation R on a set A is said to be reflexive if every element of A is related to itself. What this means is pretty straightforward. If we have a set and a relation defined on that set, for the relation to be reflexive, each element must be paired with itself. The next line formalizes this a bit. It states, in other words, for all A belonging to set A, we must have the ordered pair, A in R. Let's break that down. A represents any element within our set A. The notation A, read as a comma A, represents an ordered pair where the first and second elements are the same. So this line is saying that for every element in set A, the ordered pair, A must be present in the relation R. If even one element doesn't have this pairing, the relation isn't reflexive. Now let's look at an example. We have a set containing the numbers 1, 2, and 3. Our relation R is defined as the set of ordered pairs 1, 1, 2, 2, and 3, 3. The slide then says, to check if R is reflexive, we need to see if every element of A is related to itself. This is exactly what we just discussed. We need to verify that each element in A has a corresponding, a pair in R. Let's go through it step by step. 1 is related to 1 because 1, 1 is in R. You can see that the ordered pair, 1, 1 is in our relation R similarly. 2 is related to 2 because 2, 2 is in R. And 3, 3 is in R, so 3 is related to 3. The conclusion is, since all elements are related to themselves, R is a reflexive relation. Because we confirmed that every element in set A is paired with itself within the relation R, we can confidently say that this relation is reflexive. Now let's look at a case where a relation is not reflexive. We still have the set A equals 1, 2, 3, but this time our relation R is defined as 1, 1, 2, 2. The slide points out 1 is related to 1 and 2 is related to 2. That's true, we have those pairs in our relation. However, and this is crucial, 3 is not related to 3 because the ordered pair, 3, 3, is not in R. Because the element 3 is not related to itself, meaning the pair 3, 3 is missing from the relation, the slide correctly concludes. Therefore, R is not a reflexive relation. Remember, for a relation to be reflexive, every single element in the set must be related to itself. This example clearly demonstrates that if even one element is missing its self-pairing, the relation fails to be reflexive. In the next slide, we'll move on to another type of relation, symmetric relations, building on this foundation of understanding different relation properties. Symmetric relations. So let's move on to the next type of relation, symmetric relations. As we discussed in the previous slides, understanding these properties helps us classify and better understand relations. Now the slide states, A relation R on a set A is said to be symmetric if whenever a B is in R, then B, A is also in R. Let's break that down. Think of it like a mirror image. If A is related to B according to our relation R, then B must also be related to A. It's a two-way street. In other words, if the ordered pair, a B, is a member of the relation R, then the ordered pair, B, A, must also be a member of. Remember, this concept of symmetry will be important when we get to equivalence relations on the next slide, as symmetry is one of the key properties that defines them. So, make sure you have a good grasp of this before we move on. The slide then gives us an example. Let's consider a set containing the elements 1, 2, and 3. And let's define a relation R as the set of ordered pairs 1, 2, 2, 1, and 3, 3. Now, to check if R is symmetric, we need to examine each ordered pair. We see that 1, 2 is in R, and indeed, 2, 1 is also in R. That checks out. Next, we have 3, 3 in R now. This is a bit special. When the first and second elements of an ordered pair are the same, the symmetry condition is automatically satisfied because 33 is its own reverse. It doesn't violate the rule. Because every ordered pair in R has its reverse also present in R, we can confidently say that R is a symmetric relation. Let's look at the second example to solidify our understanding. Again, our set A is 1, 2, 3, but this time our relation R is defined as the set of ordered pairs 1, 2, and 2, 3. Now let's check for symmetry. We have 1, 2 in R, but if we look for 2, 1 in R, it's not there. Similarly, 2, 3 is in R, but 3, 2 is not. Since we find ordered pairs where the reverse is missing from the relation, we can conclude that R is not a symmetric relation. Transitive relations. So let's move on to our next type of relation, transitive relations. As we discussed on the previous slides, understanding these properties, reflexive, symmetric, and now transitive, helps us classify and better understand relations. And as you'll see on the next slide, these properties are crucial for defining something called an equivalence relation. Now the slide states, a relation R on a set A is said to be transitive if whenever a B is in R and B, C is in R, then a C is in R. Let's break that down. Think of it like a chain. If A is related to B and B is related to C, then for the relation to be transitive, A must also be related to C. It's about this chain of relationships holding true. The next line just rephrases that in simpler terms. In other words, if A is related to B and B is related to C, then A must also be related to C, same idea, just worded a bit more directly. Let's look at an example. We have a set A which contains the numbers 1, 2, and 3, and our relation R consists of the ordered pairs 1, 2, 2, 3, and 1, 3. The slide then says, 1, 2 is in R and 2, 3 is in R, so 1, 3 is in R. Let's check that. We do have 1, 2, and 2, 3 in our relation R, and look, 1, 3 is also in R. So far, so good. This confirms the transitive property for this particular combination. Now it's important to note what the slide says next. 1, 3 is in R and 3, 1 is not in R, but this doesn't violate transitivity as we only need to check if the condition holds when both a B and B, C are in R. This is a common point of confusion. We only need to check the transitivity condition when we have both pairs, a B and BC, present in the relation. The absence of 3, 1 doesn't automatically make it non-transitive. We're not required to check every possible combination. Therefore, because the condition holds true for the pairs we did check, the relation R is a transitive relation. Now let's look at a case where it isn't transitive. We have the same set of 1, 2, and 3, but this time, R is equal to 1, 2, 2, 3, and 1, 1. The slide points out, 1, 2 is in R and 2, 3 is in R, but 1, 3 is not in R exactly. We have the first two pairs, but the third, 1, 3, is missing from the relation. Since the condition for transitivity, that a C must be in R if a B and B, C, R is not met, this relation is not transitive. So remember, transitivity is all about ensuring that if A relates to B and B relates to C, then A must relate to C, and we only check this when both the initial pairs are present in the relation. Keep this in mind as we move on to equivalence relations, where all these properties, reflexive, symmetric, and transitive, come together. Equivalence relations. Let's move on to equivalence relations. As you know from the previous slides, we've been looking at different types of relations: reflexive, symmetric, and transitive. Now, an equivalence relation is special. It's a relation that combines all three of those properties. So, a relation has to be reflexive, symmetric, and transitive to be considered an equivalence relation. Why are equivalence relations important? Well, they allow us to divide a set into smaller, separate groups called equivalence classes. We won't delve into equivalence classes right now, but just keep in mind that's what they help us do. Let's look at an example. We have a set A which contains the elements 1, 2, and 3, and we have a relation R defined as the set of ordered pairs 1, 1, 2, 2, 3, 3, 1, 2, and 2, 1. Let's check if this is an equivalence relation. First, is it reflexive? Remember, for a relation to be reflexive, every element must be related to itself. Looking at R, we see that 1, 1 is in R, 2, 2 is in R, and 3, 3 is in R, so it is reflexive. Next, let's check for symmetry. A relation is symmetric if whenever we have an ordered pair, a B in R, the ordered pair B, A must also be in R. Let's take 1, 2. It's in R, and if we swap the order we get 2, 1, which is also in R. Good. Symmetry holds. Now let's check for transitivity. Remember, if we have a B and B, C in R, then a C must also be in R. Let's take 1, 2, and 2, 1. Both are in R, therefore, according to transitivity, 1, 1 must also be in R, and indeed it is. So, transitivity holds as well. Since R is reflexive, symmetric, and transitive, we can confidently say that R is an equivalence relation. Now let's look at an example of a relation that is not an equivalence relation. Again, our set A is 1, 2, 3. This time our relation R is defined as the set of ordered pairs 1, 2, 2, 3, and 3, 1. Let's quickly check for reflexivity. We need 1, 1, 2, 2, and 3, 3 to be in R, but they are. None of them are, therefore this relation is not reflexive. And because it's not reflexive, it automatically means it's not an equivalence relation. We don't even need to check for symmetry or transitivity. Remember, an equivalence relation needs all three properties to be true. Key takeaways. First, let's look at reflexive relations. This is the easiest to check. It simply means that every single element within our set, let's call it A, must be related to itself. So, for any element, a belonging to set A, the ordered pair, A must be present in the relation. Think of it as a self-loop for every element. Next, we have symmetric relations. This one deals with pairs. If we find that A is related to B, meaning the ordered pair, a B is in the relation, then a symmetric relation requires that B is also related to A. So, B, A must also be in the relation. It's a two-way street. The relationship goes in both directions. Now let's move on to transitive relations. This is where students sometimes stumble, so listen carefully. Transitivity says that if A is related to B and B is related to C, then it must be true that A is related to C. It's like a chain reaction. We need both a B and B, C to be in the relation before we can conclude that a C must also be there. Finally, we have equivalence relations. This is the big one. An equivalence relation isn't just one thing, it's actually a combination of all the others. To be an equivalence relation, a relation must be reflexive, symmetric, and transitive. If it fails on any one of those three tests, it's not an equivalence relation. These are particularly important because they allow us to divide a set into distinct, non-overlapping subsets, which we call equivalence classes. We'll explore those in more detail later. Let's recap what we've learned about these different types of relations. This slide serves as a handy summary, so pay close attention. It's important for solidifying your understanding before we move on to applying these concepts in more complex problems. So, keep these definitions in mind. we'll be practicing identifying these types of relations, and this slide will be a great reference point as we go. Are there any questions about any of these definitions before we move on to looking at some common mistakes students make? Common mistakes. So the first point here is confusing symmetry and transitivity. We've just spent time defining both of these, and it's easy to get them mixed up. Remember, for a relation to be symmetric, if you have a pair of elements related, let's say A is related to B, then B must also be related to A. It's a two-way street. Transitivity, on the other hand, is about a chain reaction. If A is related to B and B is related to C, then transitivity demands that A is related to C. Think of it as a sequence, a connection through an intermediate element. Don't look for a reversed pair like in symmetry. Look for that complete chain. Next, we have forgetting to check all elements for reflexivity. This is a really common oversight. When you're determining if a relation is reflexive, you absolutely have to verify that every single element in the set is related to itself. It's not enough to just find a few examples where it holds true. If even one element doesn't have that self-relationship, the entire relation is not reflexive. So, be systematic and check each element individually. Finally, the slide points out incorrectly applying transitivity. This is closely tied to the previous point. Transitivity only kicks in when you have both the pair B and the pair B, C present in the relation. You can't assume transitivity if one of those pairs is missing. It's a conditional statement. If a B and B, C are in the relation, then a C must also be there. Let's move on to the final slide, which highlights some common mistakes students make when dealing with these types of relations. This is really important because understanding where you might slip up is half the battle. So, keep these common pitfalls in mind as you practice identifying these different types of relations. Mastering these concepts will be crucial as we move forward and apply them to more complex mathematical ideas. Are there any of these mistakes that you think you might be prone to making, so we can focus on those specifically?